Our topic is states of matter. All the substances of matter is found in three states, or we can say three phases, that is solid, liquid and gaseous. All matter can undergo some changes, whether it may be physical or chemical composition. The factors responsible for the different behavior of solid, liquid and gases is the nature of interaction between the particles. In solid state, the particles are arranged like this, and in liquid like this, and in gases the particles are move far apart as compared to liquid and then solid. So the behavior of these solid, liquid and gases is the nature of interaction between the particles and thermal energy on the movement of these particles. The particles can move in different direction in gases, and this process is slow in liquid, and in solid they can vibrate only, they can't move. So the factors which are responsible for their behavior is intermolecular forces, the forces of attraction and repulsion causes the behavior of these particles. Intermolecular forces are the forces of attraction and repulsion between interacting particles. These particles may be atoms or molecules and are always much weaker than their chemical bonds. In chemical bond, both the atoms are sharing electrons, so these force of attraction are much more stronger than intermolecular forces. So intermolecular forces are maybe of different types. Study first dipole-dipole interaction. These force of attractions are found in between polar molecules. Polar molecules means the molecules which are already having some dipole moment, like as this is polar. Positive charge is one side and the negative charge is another side. If we take one more molecule of this type of compound, so this will be repulsion, and if this molecule is arranged like this, there will be attraction force. So this is dipole-dipole forces, and the second one is dipole-induced dipole forces. In this type of force, the one molecule has already dipole, and but another molecule is neutral. So this molecule will induce the dipole in this neutral molecule. As we know, positive charge is centered and the negative charge is around. So this molecule will induce the dipole in this neutral molecule, and it will become like this. So this is dipole induced dipole forces. These attractive forces between the polar molecule having permanent dipole and the molecule lacking permanent dipole. So it will induce the dipole force, and these forces depend on the dipole moment present in the permanent dipole and the polarizability of the electrically neutral molecule. So if it has strong dipole moment, it will induce more, and if it has less dipole moment, it will less induce this dipole force in this neutral molecule. And if this neutral molecule has more polarizability, so the more will be the dipole force. And if it has more dipole moment, in permanent, the more will be dipole force. The next is London force or dispersion forces. In this type of forces, both the molecules are neutral, but the weak attraction forces caused by instantaneous dipole-induced dipole attraction and exist all molecules and ions. These are always attractive forces. So this is our neutral molecule, this is also neutral molecule, but they will induce dipole moment and always attraction, no repulsion. This is spontaneous. Instantaneous. So these forces of attraction will be always attraction, no repulsion, and this will be a weak attraction force. Next is hydrogen bond. It is an extra strong dipole-dipole interaction found in compounds or molecules which are having highly polar hydrogen bonding. Here, oxygen is more electronegative as compared to hydrogen. Fluorine and nitrogen are also more polar as compared to hydrogen. So, the bond between this will be polar. Here, it is negative, positive, negative, positive. So, these bonds will cause hydrogen bonding in between their molecules. So the oxygen atom of one molecule will be hydrogen bonded by another hydrogen of another molecule, and here the same fluorine will be hydrogen bonded with this hydrogen and nitrogen with this hydrogen. So these force of attraction will be the cause of hydrogen bonding. The next point is thermal energy. Factors affecting states of matter is thermal energy. This energy is the energy of a body arising from the motion of its atom or molecule. If one atom or molecule is moving like this on giving thermal energy or on temperature or heating, its motion will cause thermal energy. Thermal energy is directly proportional to the temperature of substance. If we rise the temperature of any substance, the thermal energy will also increase. Intermolecular forces and thermal energy, thermal interaction, tend to keep the molecule together. Intermolecular forces of attraction, these forces keep the molecule together because of attraction, while the thermal energy will cause repulsion or movement of these molecules or atoms. So intermolecular forces tend to keep together and the thermal energy tend to keep the molecule apart. So three states of matter are the result of balance between intermolecular force and the thermal energy. If intermolecular force is greater than the thermal energy, the state of matter will be solid, and if intermolecular forces and thermal energy is almost equal or little greater, then its state will be liquid. And if the thermal energy is much more as compared to intermolecular forces, the state will be gas. So these three states of matter are the result of the intermolecular force and the thermal energy. Now we'll study gaseous state. Main characteristics of gaseous states are gases are mixture of homogeneous these are homogeneous in nature, means if we mix two or more gases, they will mix evenly and completely in all proportion. If we take gas A and gas B, if we take only 10% of A and 90% of B, the mixture will be homogeneous. Means they will mix evenly and completely. If we take A in 50% and B is also in 50%, still they will mix properly. So the nature of gases are homogeneous, means they mix evenly and completely. The next is the gases are of low density. Why gases have low density? Because the intermolecular forces in gases are very less, so they are spread apart and hence they have low density. The next is gases have high compressibility. And infinite expansibility. Means if we take a mixture of gas or any gas, and when we compress it, the molecules can come near, and this nature is called compressibility. As we know that gases filled in cylinder are how they filled, the gas molecules are compressed and then they filled in a cylinder. So the nature of gas is compressibility. And infinite expansibility means if we open the mouth of any cylinder, the molecule will move far apart in the atmosphere. We can't bound the molecules of gases in a particular environment. They will move far apart in the atmosphere, so they have infinite expansibility. If we open the mouth of container of a gas cylinder in a room, the molecules will move in that or spread in that room. And if we open that cylinder of mouth of the cylinder in an open area, so then molecule will spread in that area, so they can expand in at any limit. The next is the gas molecules exert pressure. If a gas is filled in a particular container, it will exert pressure equally in all direction. On its wall, and it will collide with another molecules, so it will exert pressure in all direction. The next is gas gases have no definite shape and volume. It takes the shape and volume of the container filled in. The next is gas molecules move rapidly. If we look at the movement of gas molecules, we can see they move in different direction in the random method. Means they have very high kinetic energy. The energy to move. So they are having high kinetic energy, so they move randomly in every direction and at high speed. The next is collision. Molecules in any container will move with high kinetic energy, so they will collide with each other. Or with the wall of container. This type of collision is called elastic collision. Gases can be liquefied if temperature is lower below the critical temperature. Below critical temperature, or if we put very high pressure, the gas can be liquefied. In gases, thermal energy is very high as compared to intermolecular forces or molecular attraction. So if we liquefy the gases, we need to lower the thermal energy. So if we lower the temperature or we apply high pressure, the gas can be liquefied. Gases undergo similar changes with the change of temperature and pressure. Gas obeys gas law. Now we'll study measurable properties of gases. These are its physical properties, and now the measurable properties. These properties can't be measurable. These are not physical properties, but these are not measurable properties. Now measurable properties are there are four parameters. First is volume, second is mass or amount of the gas, third is pressure, and the fourth is temperature. Now we'll take first volume. Volume of a gas is the how many space the gas occupies is called its volume. Entire space occupied by gas is its volume. Means volume of gas is, we can say, its volume of container. We can measure volume in units of liter, milliliter, cubic centimeter, etc. Next is mass. We can measure mass of any gas by weighing its container filled with that gas. And the empty container. The difference of weight of container filled with gas and the weight of empty container will be the result of weight of gas. The mass of the gas is related to the moles of the gas, number of moles. So the moles of gas or number of molecules will be mass in grams and its molecular weight. So this is the moles of gas is equal to mass in grams upon molecular weight. The next is temperature. Gases, when heated or when temperature is raised, gases tend to expand. If temperature is raised twice, the velocity of gases will be the square of velocity of gas will be twice. Means when we raise the temperature, the kinetic and the velocity is increases and the kinetic energy is also increases. The temperature is measured in degree centigrade. The SI unit of temperature is Kelvin, or it can be called absolute degree. We can convert any degree centigrade temperature into Kelvin by adding 273. The next is pressure. The force exerted by the gas per unit area of the wall of the container in all direction is called pressure. Force exerted by the gas per unit area of the wall of the container in all direction. So we can say P is equal to P is pressure, force upon area per unit area. We can write force as mass into acceleration this is our area. Pressure of a gas is due to its kinetic energy. Kinetic energy is half mv square of the molecule. If we increase temperature, then kinetic energy will also increase. So the pressure is directly proportional to T, means if we increase the temperature, the pressure will also increase. The pressure is measured by manometer. Manometer. If we are taking pure gas, then pressure will be measured by manometer, and if we are taking mixture of gases, then it will be measured by barometer. Unit of pressure is Pascal or Newton per meter square, or in CGS unit dyne per centimeter square, or it can be bar, or it can be atmospheric pressure, or it can be torr. These are the units of pressure. So we can measure the pressure in Pascal, Newton per meter square, dyne per centimeter square, bar, atmospheric pressure, or torr. The pressure relative to the atmosphere is called gauge pressure. and pressure relative to the perfect volume vacuum is called absolute pressure. It is relative to the vacuum. So we can say absolute pressure will be equal to gas pressure plus atmospheric pressure. When the pressure in a system is less than the atmospheric pressure, the gas pressure become negative. Atmospheric pressure in a system, this is pressure in a system. If this pressure in a system is less, this pressure in a system is less as compared to atmospheric pressure, our gas pressure will be negative. We can measure pressure by manometer. We take a container filled with gas and will connect it with an open tube. This is our mercury and this is the pressure of atmosphere and this is our pressure of gas, and this is the difference between atmospheric pressure and pressure of gas. This is H height. So we can find the pressure of gas by pressure of atmosphere plus HdG. H is this height, the difference between both the mercury level, and D is our density. And G is gravitational force. Now we'll study gas laws. The first is Boyle's law. This law is given by Robert Boyle. According to this law, for a fixed amount, means we are taking a particular amount of gas, or the amount of gas is taken as a constant, and at constant temperature. the volume of a gas is inversely proportional to its pressure. So Boyle's law states that for a fixed amount of a gas at a constant temperature, the volume of gas is inversely proportional to its pressure. So we can write V is inversely proportional to P, or we can write P is inversely proportional to V. Both are the same thing. Or P is equal to K by V. K is a constant. So P is equal to K by V, or PV is equal to K, means the product of pressure and volume of a particular gas is always a constant. Or we can say P1 V1 is equal to P2 V2 is equal to K. This situation is for two or more gases. If we are taking two or more gases, the product of pressure and volume for a particular gas will be equal to the product of pressure and volume of another gas. Means their product will be always be a constant. If we plot a graph in between pressure and volume, we can say we can write here density also. If we plot a graph between pressure and volume, or pressure and 1 by d, means one reciprocal of density, the graph will be always be a hyperbola. If we take different temperatures, different constant temperatures, the hyperbola will be like this. This is T1, T2 and T3. So the T3 will be greater T2 and T1. So for higher constant temperature, the hyperbola will have a less slope as compared to the hyperbola of lower temperature. This graph is a isothermal graph because the temperature is taken as a constant. If we plot a graph in between pressure and 1 by V, or in between pressure and density, it will be a straight line. This is for T3, T2 and T1, and T3 is greater, so it will have a steep slope, steep straight line as compared to T1. So according to Boyle's law, at constant mass or constant amount and constant temperature, density of a gas is directly proportional to P, and this is inversely proportional to V. As we know, V is equal to D by M by V, M by D. D is equal to M by V, right? Or V is equal to M by D. So we can write this, D is inversely proportional to V, and for more than one gases, we can write D1 upon D2 is equal to P1 upon P2 or V2 upon V1. There will be a constant. So we can relate the one gas to another. At altitude or at heights, the pressure goes down, hence the density is also goes down. So there will be less air at heights. So in practical life we see that mountaineers used to take oxygen cylinder with them. This is the reason why oxygen cylinder is taken by mountaineers at heights, because the pressure and density of air goes down and they feel uncomfortable in uncomfortability in breathing, so they take oxygen cylinder with them. So this was the Boyle's law. Now the second one is Charles' law. The second law of gas is Charles' law. The volume of a given mass of a gas, means a given mass or mass is taken constant. The volume of a gas is directly proportional to its absolute temperature. What is absolute temperature? Absolute temperature is the temperature plus 273 degree Kelvin. We add 273 to convert it in Kelvin, and in this law the mass of a gas is taken constant and pressure is also taken constant. Pressure is also constant for this law. So at a constant pressure and constant mass, the volume of a gas is directly proportional to its absolute temperature. So we'll say V is directly proportional to T, and if we remove this proportional sign, we'll put a constant. So V is equal to KT, or we can say V is equal to K T degree centigrade plus 273. Or for more than one gases, V1 upon V2 is equal to T1 upon T2, or V1 upon T1 is equal to V2 upon T2, that will be constant for two or more gases. If temperature is taken 0 degree centigrade, then volume will become V0. So if we put this value in that equation, it will say V0 is equal to K into 273.15, or K will be V0 upon 273.15. When we put the value of K in this equation, the V will become V0 upon 273.15 and T plus 273.15. So here we put this value of K here in this equation, and it becomes V is equal to V0 upon 273.15 and T plus 273.15. Now we'll solve this equation. V is equal to, we'll take V0 common, and 1 plus T upon 273.15, or V0 will be 1 plus alpha Vt. So the value of alpha V is equal to alpha V is a volume coefficient, and we can say alpha V is equal to V minus V0 upon TV0, and it will, on solving, it will become 273.15 or 3.66 into 10 to the power minus 3 degree per centigrade. Thus, for every 1 degree temperature rise, on rise of 1 degree centigrade temperature, the change caused volume by 1 by 273.15 of volume at 0 degree centigrade. Means if we rise the temperature by 1 degree, the volume will rise by 1 by 273.15. If we plot a graph in between volume and temperature, it will be like this. As we know that volume is directly proportional, so it will be a straight line, or we can take here density also. As we know, volume is inversely proportional to density. So if we take volume or 1 by d against t, it will be a straight line. But if we extend this graph, or this is our T degree centigrade, here it is in Kelvin. This is minus 273.15 degrees centigrade, and this is the lowest possible temperature because at this point volume becomes 0. So this is lowest possible temperature. So where volume of a gas becomes 0 is known as absolute zero temperature. So the absolute zero temperature is minus 273.15 degrees centigrade. As we know, V is equal to m by d. We can say d is inversely proportional to t, or it is inversely proportional to V. So we can write d1 upon d2 is equal to t2 upon t1, or v2 upon v1. Here again it is a constant. The use of the Charles law is we can see in hot air balloons. In hot air balloons in sports, when temperature is raised, means the air is hot, the volume of balloon or gas increases. So balloons are expanded, and this law is applied in hot air balloons. Now the next law is Gaseous law. Gaseous Gay-Lussac law or Hamilton's law. It is also known as Hamilton's law. According to this law, the pressure of a given mass of a gas is directly proportional to absolute temperature. Means the amount of gas is taken as a constant and the volume is also taken as constant. So a particular amount of a gas and at constant volume, the pressure of a gas is directly proportional to its absolute temperature. So we can write P is directly proportional to T and we can solve it. P is equal to KT, where uh, T is Kelvin. In Kelvin, we can say T degrees centigrade plus 273.15, or we can write K is equal to P upon T, or we can write P1 upon P2 is equal to T1 upon T2, or P1 upon T1 is equal to P2 upon T2. These are constant for two or more gases. If we compare two or more gases, the of pressure and temperature will be always constant. If T is taken 0 degree centigrade, then P will become P0 and P0 will become K into 273.15, or K value of K will be P0 upon 273.15, and then putting in this equation P is equal to KT, when we put this the value of K here, it will become P is equal to P0 upon 273.15 and T will become T plus 273.15, or P0 plus 1 plus T upon 273.15, or we can put an coefficient alpha P T, and alpha P will become, it's a pressure coefficient, and alpha P will become P minus P0 upon T P0. On putting the value, it will become 273.15 or 3.661 into 10 to the power minus 3 per centigrade. So for every 1 degree change in temperature, the pressure of a gas changes by temperature changes by 1 degree centigrade. It will cause the change in pressure by 1 upon 273.15 of the pressure at 0 degree centigrade. So if we raise the temperature by 1 degree centigrade, the pressure will be increased by 1 upon 273.15 at 0 degree centigrade. And If we lower the temperature by 1 degree centigrade, the pressure will become lower as compared to 1 by 20 273.15 as compared to 0 degree centigrade at the pressure of 0 degree centigrade. So if we draw a graph in between pressure and temperature, here we are taking in Kelvin scale, it will be a straight line. If we plot that graph in between pressure and temperature at different volumes, it will become like this. Where V3 is taken greater as compared to V2 and V1. At different constant volumes, the graph between pressure and temperature will become a straight line. If we take the constant volume, higher constant volume, the graph will be the straight line will be having a lower slope as compared to lower volume. These type of graphs are called isochore. Now the next gas law is Avogadro's law. According to this law, equal volume. Here we are taking equal volume, means volume is taken as constant. Equal volume of any two gases at the same temperature. Temperature is taken constant and pressure. Pressure is also taken as constant. The equal volume of any two gases of the same temperature and pressure contain the same number of molecules, means volume is directly proportional to N at constant temperature and pressure. So we can write V is equal to Kn, or V is equal to K by N. Here N is the number of moles of gases, V is volume and K is constant, or we can write V1 upon N1 will be V2 upon N2. V is directly proportional to N, or we can say V is equal to Kn. So we can write V1 upon N1 is equal to V2 upon N2. It's a constant for two or more gases. So 1 mole of any gas contains the same number of molecules, and by the law it must occupy the same volume at a given temperature and pressure. Means if we are taking temperature and pressure as a constant, one mole of a gas will be having the same number of molecules. We are taking same number of molecules as Avogadro number. That is Avogadro number is 6.023 into 10 to the power 23 molecules, and by this law it must occupy the same volume. If we are taking same number of moles of two gases, their volume will be same, because here pressure and temperature both are constant, so the number of moles will be same and volume will be same. So the volume of 1 mole of a gas is called molar volume. volume of 1 mole of a gas is called molar volume, and is measured, which is equal to 22.4 liter per mole at STP. So the molar volume at STP is 22.4 liter per mole. So these were the gas laws. Now we'll study ideal gas equation. According to Boyle's law, P is inversely proportional to V at constant temperature and at constant number of moles. According to Charles' law, V is directly proportional to at constant pressure and at constant number of moles. And according to Avogadro's law, volume is directly proportional to N number of moles when pressure and temperature is taken constant. By combining all these three laws, we get V is directly proportional to NT by P. When we combine these three laws, we get V is proportional to NT by P. When we remove this proportional sign, we'll get V is equal to nRT by P. Here R is ideal gas constant, because an ideal gas can follow all these three laws. So when we combine all these three laws, we get V is equal to nRT by P, and this proportional sign removing, we get a constant that is called ideal gas constant. So we'll get the equation PV is equal to nRT, and this is called ideal gas equation. Ideal gases follow this type of this equation and by isothermal and adiabatic processes. So the gases which follow or which obey ideal gas equation is called ideal gases, and these gases follow this equation at all conditions of temperature and pressure. So at all temperature and pressure, they will follow ideal gas equation, and these gases will be called ideal gas equation. Now by combined gas law, for two or more reaction gases, we can say P1 V1 upon T1 will be equal to P2 V2 upon T2. That will be a constant, and R, the value of R will be PV upon T and T, and the unit will become pressure, and this is volume, this is number of moles, and this is our temperature. We can say pressure force upon area. This is our volume, and it will become moles into temperature. We can cut by this volume and area. It will remain force into length. As we know, area multiplied by length will become volume. It will become moles into temperature. We can write force into length as energy. Energy upon moles into temperature. So the unit of ideal gas constant will become energy. The unit of energy is joule or whatever. So the unit will become energy ka unit, and per mole, this is per mole, we can say in mole inverse, and Kelvin inverse. So the value of R will become for ideal gases 1.99 calories. We are taking calories, unit of energy is calorie, and per mole per Kelvin, or if we take it in joule, it will become 8.3143 joule per mole per Kelvin. The gas constant R for a single molecule will be called Boltzmann constant. Constant K. So the K will be R by N, and we can keep the value of here R. We are taking 8.3143 and and the value of N is Avogadro number 6.023 into 10 to the power 23, and we are taking it in ergs, so 10 to the power 7. So it will become its value will become, it will come in ergs per mole per degree. Now PV is equal to nRT. We can write the N is equal to M upon capital M, that is number of moles is equal to mass upon molecular weight. ये number of moles, so it will become M upon capital M R T, and as we know density is equal to mass upon volume, so we can keep the value of density here, so it will become and it will become, this is PV is equal to dV RT upon M, it will become m is equal to v से v कट जाएगा and it will become dRT upon p, or we can write dt upon p is equal to m upon r. Here m and r both are constant, so we can say d1 t1 upon p1 is equal to d2 t2 upon p2. It's a constant for two or more gases. Now the gas density of density of gases is different as compared to solids and gases, solids and liquids. How they are different? As we know, gas densities are generally stated in gram per liter, whereas the density of solids and liquid are measured in grams per centimeter cubic. The second is the densities are depend on temperature and pressure. In gases, while in a liquid and solids, it can be dependent on temperature but not on pressure. But in solids and liquids, the densities are dependent on temperature on a little extent, but it's not depend on pressure at all. So in gases, the densities are dependent on temperature and pressure, but in solids and liquid, it is dependent on temperature at a little extent, but it's not dependent on pressure at all. The next difference between densities of gas and solids and liquids: densities of gases are directly proportional to molar mass of gas. In gases, but in liquid there is no direct relation between density and the molar mass. So these are the differences of densities of gas and solids and liquid. Our next topic is Dalton's law of partial pressure. According to this law, when two or more gases which do not react chemically are kept in a closed vessel, the total pressure exerted by by the mixture of gases is equal to the sum of partial pressure of individual gases. See, this is a closed container and this is a gas 1, this is gas 2, and if this is gas 3. So the pressure for different gases, suppose it's P1, the pressure exerted by this gas is P1, if it is P2, and if it is P3, then the total pressure or P total will be equal to P1 plus P2 and plus P3, or if we have more than 3 gases, it will be added, so on. Here P1 is the partial pressure of gas 1, P2 for gas 2, and P3 for gas 3. Now we'll see what is the partial pressure. Partial pressure is the pressure exerted by a gas when it is filled in a container alone. So the pressure exerted by this gas is partial pressure. So we'll define it. The pressure exerted by a gas when it is present alone in the same container. And at the same temperature. Means we can find the partial pressure by studying when the gas is filled in the same container. Both the containers should be same and the temperature condition should be same. At that time, the pressure exerted by that particular gas is called partial pressure. Partial pressure of a gas P1 is equal to number of moles. The formula for the partial pressure is number of moles of the gas and P multiplied by total and total number of moles in that mixture. So partial pressure can be calculated by this formula: number of moles of the gas into P total divided by total number of moles in that mixture. These total number of moles are the total number of moles of all the gases in that mixture. So we can write number of moles of the gas divided by total number of moles in that mixture. We can write it mole fraction x1 multiplied P total. If the number of mole of gases, number of moles of gases having volume V1, V2, V3 and so on Vn at pressure P1, P2, P3, Pn, when these number of moles are mixed together in a container of volume V, it's volume of container, then P total will be P1 V1 for gas 1, P2 V2 for gas 2, P3 V3 and so on, and will be divided by the total volume. Total volume is the volume of container. As we know, PV is equal to nRT, so we can write N1, N2, N3, or and we'll put this value RT by volume, or we can say P total is, as we know that number of moles is N1 plus N2 plus N3, so we can write here N, total number of moles, nRT by V. So we'll get this formula for calculating the total pressure exerted by the mixture of gases in that particular container. Now the application of this law, Dalton's partial pressure law, is we can calculate the mole fraction of a gas x1 in a mixture. This is partial pressure of a gas P1 will divided by P total, so we'll get the mole fraction. Next application is we can calculate percentage of a gas in the mixture. It will be by partial pressure By this formula we can get percentage of a gas in the mixture. Next application is pressure of dry gas collected over water. When a gas is collected over water, this is our water and this is our gas. So the pressure exerted by this moist gas will be its own partial pressure at the same temperature of the gas plus the water pressure, pressure of water vapor. So when a gas is collected over water, it becomes moist because of this water, which exerts its own partial pressure at the same temperature of the gas. So this partial pressure of water is called aqueous tension. And the pressure of dry gas can be calculated by removing aqueous tension. So we'll remove aqueous tension from P moist or P total, and we need to remove this P water vapor or aqueous tension. Now, by this law, Dalton's partial pressure law, the one more application is there. We can get relative humidity. At a given temperature, the relative humidity will be given by this formula: partial pressure of water in air divided by vapor pressure of water. So we can get relative humidity by this formula. The next is, so these are the application of partial pressure law. Now the limitation of this law. This law is only applicable when gases do not react chemically. Then this will law be applied. But these reactions are these gases are nitrogen and oxygen, mixture of nitrogen and oxygen, which do not react chemically. We can say carbon monoxide and carbon dioxide. But for the gases who react chemically, as hydrogen and chlorine, mixture of this reaction, these gases, and carbon monoxide and chlorine, these reactions are these gases are chemically reactive. Means the mixture when the mixture of these gases, when put in a container, these gases react with each other. So the Dalton's partial pressure law will not apply for these gases. So This is the limitation of this law. Now the law of partial volume. This law is given by Amagat. According to this law, when two or more gases do not react chemically, when kept in the closed container, the total volume exerted by the mixture will be equal to the sum of the partial volume of individual gases So we can write the V total will be equal to V1 plus V2 plus V3, the partial volume of n gases. Now Graham's law of diffusion and diffusion. And effusion. What is diffusion? First, the process of spontaneous spreading and intermixing of gases to form a homogeneous mixture is called diffusion. If we take 3 different types of gases in a container and we open those mouth, these gases will mix evenly . So the process of spontaneous spreading and intermixing to form a homogeneous mixture against irrespective of force and force of gravity, means in mixing of these gases there will be no effect of gravity and the gases will intermix with each other evenly. So this is the diffusion. And now what is effusion? When we take a container filled with gases, now the escape of the gas molecules from this container, from the tiny hole of this container, is called effusion. So there's a difference in between diffusion and effusion. The diffusion is the process of spontaneous intermixing of gases to form a homogeneous mixture, and the effusion is the escape of gas molecules from a tiny hole. So diffusion and effusion is done. Now all the gases spontaneously diffuse into one another when they brought into contact. All the gases diffuses when they brought in contact. Next is diffusion into vacuum. Takes place much more rapidly as compared to the another places. Means in vacuum the diffusion takes place very fast as compared to another places. Now rate of effusion and diffusion depends on its molar mass. As we know, the speed of lighter gas is fast as compared to the speed of heavier gases. So lighter gases will diffuse very fast as compared to heavier gases. Hydrogen gas has the highest rate of diffusion. According to Graham's law of diffusion and diffusion, it states that at constant temperature and pressure, the rate of diffusion or the rate of effusion is inversely proportional to the square root of vapor density So we can write the rate of diffusion R is inversely proportional to the square root of its density, vapor density, or we can write for two gases the rate of diffusion of for one gas divided by rate of diffusion for another gas will be R1 by R2 will be the square root of D2 upon D1. This is the comparison for two gases. If we are taking two gases, as we know, the molecular weight is equal to twice of vapor density. So we can write here R1 upon R2, the square root of D2 upon D1, or we can write it like this, D2 into 2, D1 into 2, or we can write the molecular weight M2 upon M1, the square root of this. We write the rate of diffusion is equal to volume of a gas diffused divided by time taken for the diffusion. So we can write the formula for the comparison of two gases. We can write it like this, or we can write in the form of density. So we can write the rate of diffusion by these formulas. For the gases, for two gases, we can write it V1 upon V2 is equal to N1 upon N2, the number of mole of gases, or we can write N1 upon N2 if we take the case 1 where T1 is equal to T2, time taken to diffuse is equal, and as we know N is equal to W by M, weight of a gas divided by molecular weight. So we can write it this formula by W1 upon M1 into M2 upon we can write it again, W1 upon M1 multiplied by M2 upon W2 will be M2 upon M1, or we can say M2 W1 M1 W2 will be equal to M2 upon M1. We'll shift it here and we'll get W1 by W2 will be M1 upon M2. If we are taking T1 is equal to T2, we'll get W1 by W2, that is a mass of a gas is inversely proportional to the square root, directly proportional to the square root of molecular weight. If V1 is equal to V2, the volume of gases diffused, the volume of the gases getting diffused is equal, then the rate of diffusion will become like this. And if in case 3, if T1 is equal to T2, the rate of diffusion is directly proportional to the pressure, and as we know rate of diffusion is this, so the rate of diffusion will become in the form of pressure will get this equation. Now, application of this law. By the Gram's law of diffusion, we can get vapor density and molecular weight by these formulas. Weight of gases and the second application is to prepare Ousley's marsh gas indicator. Which is used in mines to find out if any gas is getting diffused or any poisonous gas is getting diffused. We can use this indicator in mines. Our next topic is barometric distribution law. For gaseous system, the gravitational force is negligible. But this is not true for all the gases of high molecular masses. As we know, the gases are very light in weight, so the gravitational force is negligible. But with high molecular mass, such as polymers, which have high molecular mass, the gravitational force is not negligible. So the variation of pressure with altitude is given by the barometric formula. What is barometric formula? P is equal to P naught E minus mgh upon RT. Here P naught and P is the respective pressure of gases. This is at the ground level pressure, and P is the pressure at height h. And m is molecular mass of that gas, and g is acceleration due to gravity, and T is temperature in Kelvin. So at altitudes we can find out the pressure by this barometric formula. As we know that P is directly proportional to D and this is also directly proportional to N, we can write the formula for density and number of moles as well as. So it will become D is equal to D naught E minus mgh upon RT, or for number of moles it will become N naught E minus mgh upon RT. So these are the formulas for density and for the number of moles, or we can write in the form of logs. Log P upon P naught will be equal to log D upon D naught, or log N upon N naught, and its value will become minus 1 by 2.303 mgh upon RT. So this is the barometric formula for gases at altitudes. Now the kinetic theory of gases. This theory is developed by some scientists, Bernoulli, Maxwell, Joule, Clausius, and Boltzmann. It represents the dynamic particles like particles or microscopic model. It is for different gases. They suggest the dynamic particle or microscopic models for different gases. The postulates of this theory are: for every gas consists of a large number of small particles. Means gases are made up of small number of particles. Those are moving with high speeds. So first postulate is small particles with high speed. And this speed is very high and in different directions. In all possible directions they move. It can be up, down, or randomly. Now the second is the volume of the individual molecule is negligible as compared to the total volume. Means total volume is much more as compared to the individual volume. Volume of gases, or we can say it's negligible. Next postulate is gas molecules are perfectly elastic. Means if they collide with each other, they will not lose their kinetic energy. No loss of kinetic energy due to collision. So gas molecules are perfectly elastic. Effect of the gravity on the motion of molecules is negligible. No effect. The next is Gas molecules are considered as point masses, and because they do not have potential energy. No potential energy. So they are very small in mass, so they will not have potential energy. The next is if gas molecules are not having potential energy, so the attractive and repulsion forces between the molecules are negligible. No attraction and repulsion. The pressure is due to continuous bombardment of molecules on walls of the container will be the cause of pressure. These molecules of gases are continuously bombarding or hitting the walls of the container will induce the pressure of this gas, will be the reason of the pressure of this gas. At a constant temperature, next postulate is at constant temperature the average KE, the average kinetic energy of all gases will be same. If the temperature is constant, then all the gases will have the same average kinetic energy. The average kinetic energy is directly proportional to absolute temperature. Now, on the basis of these all postulates, the gas equation is derived as PV is equal to N1 by 3 Mn C square, CRMS square, where M is average mass of a molecule, N is number of molecules, CRMS is the root mean square, velocity of the gas. Root mean square velocity of the gas. So according to kinetic theory, the postulates of kinetic theory of gases, we derived a formula that is PV is equal to 1 by 3 MnCRMS square. For one molecule of gas, the kinetic energy will become will 1 by 2 mc square, and for n number of gases it will become n molecule of gases, it will become 1 by 2 n mc square. As we know that PV is equal to 1 by 3 MnC square, so we will put the value of PV here. It will become 3 by 2 of PV and if the n is 1, if we take one molecule of gas, then it will become 3 by 2. As we know, PV is equal to RT and N is equal to 1, then it will become 3 by 2 of RT. On putting the value of these constant, we'll get 3 by 2, 8.314 into T, and this will become 12.47 T temperature, and the unit will become joule. So the average kinetic energy per mole divided by n is Avogadro number, it will become 3 by 2 of RT by N, or we can say 3 by 2 of KT, where K is Boltzmann constant. This equation shows the kinetic energy of translation of a gas depends only on the absolute temperature. This is known as Maxwell generalization. So the average kinetic energy depends only on absolute temperature. If T is taken 0 Kelvin, means minus 273.15 degrees centigrade, then average kinetic energy will become 0. Thus, absolute 0 is the temperature at which molecular motion ceases. At absolute 0 Kelvin, the motion ceases, means no motion is there, no kinetic energy is there. Now, molecular collision. Our next topic is molecular collision. What is a molecular collision? Molecular collision, the closest distance between two molecules it can be this or it can be this. The closest distance between the center of two molecules is called molecular or collision diameter. Or molecular diameter. The molecular diameter of all the gases is nearly same, in the range of 10 to the power minus 8 centimeter. Average. The number of collision taking place in unit time per unit volume is called collision frequency. Number of collision per unit time and element per unit volume. And it is expressed by Z. During molecular collision, a molecule covers a small distance, and this average distance covered by molecule is called mean free path. So this is our molecule 1, molecule 2, and if travels this distance, this distance traveled by molecules between two successive collision is called mean free path. And it is given by lambda. According to kinetic theory of gases, mean free path that is lambda is proportional to T and inversely proportional to P. So the larger size of the molecule the smaller the free mean path, means lambda is inversely proportional to its radius square. Greater the number of moles per unit volume, the number of molecules per unit volume, smaller the mean free path. As we know that number of molecules are greater, they will collide with each other in very less time. So the path will be small, the mean free path will be small. So, and if temperature is raised, at high temperature, the lambda will be high, and if the pressure is higher or pressure is raised, the lambda will be small or lower. So we can write the relation between collision frequency and mean free path is, this is our collision frequency, will be equal to CRMS, that is root mean square velocity divided by lambda. This is the relation between collision frequency and the mean free path. Now the molecular speeds or velocities. How many types of molecular speeds or velocities are there? As we know, at any particular time, all the molecules do not possess same speed. It can be high, it can be slow, or whether it can be medium. So all the molecules uh, at the particular time do not possess same speed due to its uh, collision. If two molecules are colliding with each other, their speed can be slow or it can be high, depends on their molecular weight. So all the molecules do not possess same speed, and their direction direction and speed are changing continuously. After collision, they change their direction, so their direction is also changeable. According to Maxwell, at a particular temperature, the distribution of distribution of speed remains constant. At a particular temperature. And this is known as Maxwell-Boltzmann distribution. Types of molecular speeds or velocities. First is root mean square velocity. That is CRMS. It is the square root of the mean of the square of the velocities of a large number of molecules of the same gas and is given by the formula the square root of the mean of the square of the velocities of a large number of the molecule of the same gas is called root mean square velocity, and is given by CRMS is equal to C1, C2, C3 are the different velocities of different type of gases, different molecules, and the number of molecules. We can write it like this: 3 PV upon or we can write it in the form of RT, or we can write in the form of KT. As we know, M and 0 is M, K is the Boltzmann constant. As K, the value of K is R by N0, so we put the values here, or we can write the root mean square velocities ratio for two gases. For the same gas at different temperature. This is for same gas at two different temperature, and we can write the CRMS ratio if we are taking two different gases at same temperature. At same temperature. If we need to find out the CRMS ratio for the same gas at different temperature, will determined by this formula, and if we are taking the different gases, we'll get the CRMS ratio by this formula. Now the second type of velocity is average velocity. Or C average. This is the average of velocity possessed by the molecules, and we'll find out by C average and different velocities, the addition of different velocities divided by the number of moles or molecules. This is C average, or we can write it like this also, 8 RT upon pi m, or we can write 8 kT upon pi m. So these are the formulas for C average. Now the third type of velocity is most probable velocity. Yes, CMP. As the name is suggesting, the most probable velocity is the velocity possessed by maximum number of molecules. At a given temperature. So we can find out CMP, most probable velocity, by the formula 2RT upon m, or we can write 2PV upon m, or in the form of density we can write 2P by D. So these are the formulas to find out the CMP, most probable velocities. The relation between molecular speeds, different types of speeds. So here is our CMP, and 8 RT upon pi m, this is our C average, and 3 RT upon m is our CRMS. And when we solve these or simplify these formulas, these values will get will get 1 is to 1.128 and 1.224. This is our CMP, this is our CAV, and this is CRMS. So the ratio between CMP, C average and CRMS is 1 is to 1.128 is to 1.124, or we can say the CRMS is greater than CAV and CAV is greater than CMP. So these are the ratio of different types of speeds. Now the next topic is real and ideal gases. Gases which obey the gas laws obeying gas laws or we can say gas law or ideal gas equation. Ideal gas equation is PV is equal to nRT. The gases who follows this gas equation or this ideal gas equation or gas laws at all temperature and pressure are called ideal gases or perfect gases. But almost all gases do not follow this law or they deviate from the ideal behavior. Those gases are called real gases. Means no gas is perfect to follow the ideal gas law, or we can say no concept of perfect gas is only theoretical. The gases tend to show ideal behavior only at a higher temperature. Temperature is higher above their boiling point. So the gases tend to show ideal behavior more and more as temperature rises or raises above the boiling point of their liquid forms, and pressure is lowered. So there's a condition to shift their behavior from real gas to ideal gas. We need to raise the temperature and we need to lower the pressure. So only in those conditions the real gases will show the behavior of ideal gases. The deviation can be displayed by the plotting PV isotherm of real and ideal gases. Here is the graph. This is our compression constant. This is our P. Here Z is equal to 1. Only some gases like hydrogen and helium show the straight line. This is for oxygen, nitrogen, methane, and carbon dioxide. The term this PV by nRT is called compression factor. That is Z, and suitable for a quantitative description of the deviation from the ideal gas behavior. Now, the greater is the departure of Z. Here Z is equal to 1. Here Z is negative and this is, here it is positive. So, if the greater is the departure of Z from the unity, the more is the deviation from ideal behavior. So only the gases having Z is equal to 1 will show ideal gas behavior. At all temperature and pressure. Such as nitrogen. Nitrogen has Z nearly 1 at 50 degrees centigrade. So this temperature is known as Boyle's temperature, because the nitrogen is showing ideal gas behavior. So this temperature is called Boyle's temperature or Boyle's point. That is TB. But this shows an appreciable range of pressure, not all, at all the pressure. If Z is greater than 1, the gas is less compressible than expected from ideal behavior and will show the positive deviation. And this happens usually at high pressure, that is PV will be greater than RT. If Z is less than 1, gas is more compressible. And the deviation will be negative. And it happens only at usually at low pressure. And in that case, it will become PV is less than RT. So for the ideal gas behavior, Z should be 1, and it happens only for a particular range of pressure. And if Z is greater than 1, then gas is less compressible and it will show the positive deviation. Here it is showing positive deviation. And if Z is negative, then it will show the negative deviation. Here it is negative deviation, here it is positive deviation. The Z is greater than 1 is in gases hydrogen and helium. Z is greater than 1 for hydrogen and helium at all temperature and pressure range. So they will show always positive deviation. here they are always Z is always 1 at all temperature and pressure, so they will always show the positive deviation. The most easily liquefiable and highly soluble gases like ammonia and sulfur dioxide, these gases are easily liquefiable and highly soluble. This shows larger deviation from ideal behavior, means the Z is very less than 1. Some gases like carbon dioxide show both positive and negative deviation. Here carbon dioxide, here it is negative deviation and here it is positive deviation. So some gases show both the deviation, negative and positive as well as. Now we'll study the causes of deviation of real gases from ideal behavior. The ideal gas laws can be derived from the kinetic theory of gases, which is based on two assumptions. First, the volume. The volume occupied by the molecules is negligible as compared to the whole volume, the total volume. And the next is the molecule exerts no force of attraction upon one another. So these were the two assumptions on which kinetic theory of gases are given. Both the assumptions are not applicable to real gases. Not applicable because the real gases do not show these assumptions because the molecules, the volume of molecules are not negligible and they feel the force of attraction between them. So real gases deviate or show deviation from ideal gas behavior. To overcome these deviation, the van der Waal gives the equation for real gases. This is called van der Waal equation. To rectify the errors of ignoring the intermolecular forces, of attraction and volume occupied by the molecules, the ideal gas equation by van der Waal is given, and it introduces two corrections for intermolecular forces and volume occupied is introduced or given. First is volume correction. and the second is pressure connection. This van der Waals equation is obeyed by the real gases. At a wide range of temperature and pressure, not at particular temperature or pressure. So this equation is called equation of state for the real gas. Equation of state for the real gas. The equation for n moles of gas is given by P plus n square upon a upon V square. This is the correction in pressure, and V minus NB this is the correction in volume, is equal to nRT. This is pressure correction. This correction is for intermolecular attraction, and this is volume correction. Volume correction for finite size of molecules. A and B are van der Waals constants. Which depend on nature of gas. Normally A is very greater than B for a gas. Constant A is indirect measure of attractive forces between molecules. If A is very greater, then it will be more easily the gas can be liquefied. Example are sulfur dioxide, ammonia, hydrogen sulfide, carbon dioxide. These are easily liquefiable gases. So they have high A van der Waals constant for pressure, and for permanent gases like nitrogen, oxygen, hydrogen, and helium, these are having low A. Then these gases will not be easily liquefiable. Units of A is atmosphere liter square mole minus 2. This is the unit for van der Waals constant A. Now constant B or volume correction. This is called co-volume or excluded volume. If the value of B is greater, larger is the size of the gas molecule, If B is less, the smaller is the volume. The unit of B is liter per mole. Relation between van der Waals constant and Boyle's temperature. And Boyle's temperature. TB, this is Boyle's temperature or boil point, is equal to A upon BR. This is the relation between Boyle's temperature and van der Waals constant A and B. Now, van der Waals equation at different temperature and pressure. When pressure is extremely low, for 1 mole of gas, we can write the van der Waals equation by P plus A by V square, and V minus B is equal to RT. On solving this equation, it will become PV is equal to RT minus A by V plus P by B and AB upon V square. At extremely low pressure, the van der Waals equation becomes like this. When pressure is extremely high, for 1 mole of gas, it will become PV is equal to RT plus PB, or we can write PV upon RT 1 plus PV by RT. As we know, PV by RT is Z, our compressible factor, or we can write like this: Z is equal to 1 plus PV by RT. Z is compressible factor. So at higher pressure, the van der Waals equation becomes like this: Z is equal to 1 plus PV by RT. Now, these were the conditions when pressure is very high and very low. When we keep temperature changing, temperature is very high, then for 1 mole of gas, the the van der Waals gas equation becomes PV is equal to RT. And the next is temperature. When temperature is very low, and for 1 mole of gases, the equation will become P plus A by V square V minus B is equal to RT, or PV is equal to RT or TR plus PB minus A by V plus AB by V square, or so on solving it will become PV by RT minus A upon V RT, or as we know PV by RT is Z, our compressible factor, it will become 1 minus A upon V RT. So the van der Waals equation will become like this for when temperature is very high. For hydrogen, As we know that molecular mass is small, so our van der Waals constant A will be small. It is due to because of small intermolecular forces in between. So, due to small intermolecular forces, the van der Waals constant A will be small. Hence, our van der Waals equation will be like this: as A is small, A by V and AB upon V square. Value of these will be negligible, and hence it can be ignored. So our van der Waals equation will become PV is equal to RT plus PB, and we can write PV upon RT will be 1 plus PB upon RT, or PV by RT is our compressibility constant, so we can write Z is equal to 1 plus PB upon RT. For hydrogen, Z will be always greater than 1. Now we'll study merits of van der Waals equation. Van der Waals equation is good for real gases. It is good for real gases up to moderately high pressure. If pressure is low, then it will not be good. It will give some more results, different results. The equation represents the trend of the isotherm, representing the variation of PV with P for various gases. So we can study isotherm effect. Next is, by this equation, it is possible to obtain the expression of Boyle's temperature. Critical constant and inversion temperature. So the next is, it is useful in obtaining a reduced equation of state. So these are the merits of van der Waals equation. This is good for real gases up to moderately high pressure. And isotherm effect can be get PV versus P for various gases. We can get the values of Boyle's temperature, critical constant and inversion temperature, and it is useful in obtaining a reduced equation of state. Now limitations of van der Waals equation. This equation shows appreciable deviation at low temperature and to high pressure. So if we are having a very low temperature and high pressure, we'll get appreciable deviation. In that case, we can't use this van der Waals equation. Next is A and B do not remain constant over the entire range of temperature and pressure. So this equation is valid only over specific range of temperature. Specific range of temperature and pressure. Now, what is critical state? The critical state a state for every substance at which the vapor and liquid state are indistinguishable. So, this is the state, the critical state is the state where vapor and liquid state of any substance of vapor and liquid states are indistinguishable from each other. So this state is called the critical state of matter, critical temperature. It is known as TC. Critical temperature is a temperature above which the gas cannot be liquefied. The temperature above which gas cannot be at this temperature, if pressure is large pressure is applied, then after that it can't be liquefied. So you can write, if large pressure is applied, so above this temperature the gas cannot be liquefied. If pressure is applied also, then it can't be liquefied. So we can write the formula for critical temperature is Tc is equal to 8A upon 27 Rb. A and B are van der Waals constants. Critical pressure. Critical pressure is the minimum pressure which must be applied to a gas to liquefy. It is known as Pc, and the value of Pc is A by 27B square. By these formulas we can calculate the critical temperature and critical pressure. So critical pressure is the pressure above which a gas cannot be liquefied, and critical pressure is the minimum pressure which must be applied to a gas to liquefy. Critical volume. It is known as Vc, and it is the volume occupied by by 1 mole of a substance at its critical temperature and critical pressure, and the value of critical volume is 3b. So critical volume is the volume occupied by 1 mole of a substance at its critical temperature and critical pressure. Now critical compressibility factor. The value of critical compressibility factor is Zc is equal to Pc Bc upon Rtc. By putting the values, we will get the value of critical compressibility factor as 0.375. A gas behave as van der Waals gas if its compressibility factor Zc is value is equal to 0.375. In that case, a gas will behave like a van der Waals gas. A substance in the gaseous state below Tc, that is below critical temperature, is called vapor, and above Tc it will be in gas state. So a substance in the gaseous state below Tc is called vapor, and above Tc it will be called a gas. Now next is degree of freedom of a gaseous state or gaseous molecule. Motion of a molecule is described in terms of degree of freedom, and these degree of freedom is are of three kinds of motion in it. Is the result of the three kind of motion. First is the translation motion. When a molecule travels from one place to another, this is by this motion will cause different type of degree of freedom. This is the translation degree. Next is rotational motion. It is because of this degree of freedom is because of the rotation of molecule. And the third is vibrational motion. When a molecule vibrates, it will cause a degree of freedom. So the motion of atom is generally described in terms of the degree of freedom which they possess. When a gaseous molecule is heated, the energy supplied to it may bring different types of motion. The translation motion, which is happened from one place to another, And second is rotational motion. In this kind of motion, molecule rotates on its axis. Or and the third one is vibrational motion. After heating, it will get some kinetic energy, and because of that kinetic energy it will vibrate. So these are the motions because of degree of freedoms of a gaseous molecule occurs. Or we can say molecule possess translation, rotational or vibrational degree of freedom. For a molecule, for a molecule made up of n atoms, n atoms or number of atoms are n, total degree of freedom will be 3n, and these 3n will be our translation, rotational and vibrational degree of freedom. If a molecule is its shape is linear, then the translation degree of freedom will be 3, rotational degree of freedom will be 2. So left is 3n minus 5. The vibrational degree of freedom will be 3n minus 5. For a non-linear molecule, the translation degree of freedom is 3, rotational is also 3. So the left is 3n minus 6, vibrational degree of freedom. Now the next topic is specific and molar heat capacity of gases. Specific and molar Now, what is specific heat? Specific heat of a substance is the quantity of heat this heat can be in form of calories, joule, kilojoule or kilocalories, required to raise the temperature by 1 degree centigrade by the to raise the temperature by 1 degree centigrade of 1 gram of that substance. 1 gram of substance is called specific heat of that substance. It is at constant pressure. The specific heat is Cp, and at constant temperature volume it is Cv. So the specific heat of a substance is the quantity of heat required to raise the temperature of 1 gram of that substance through 1 degree centigrade. This is called specific heat, and the Cp is specific heat at constant pressure, and the Cv is specific heat at constant volume. Now, molar heat capacity. Molar heat capacity of a substance is the quantity of heat required to raise the temperature of 1 mole of the substance by 1 degree centigrade. Heat required to raise the temperature of 1 mole of substance by 1 degree centigrade temperature is called molar heat capacity. Now, the relation between molar heat capacity and specific heat capacity is molar heat capacity is equal to specific heat capacity into its molecular weight. Molar heat capacity is noted by CV. For at a constant volume, it will be into CV into M. This is capital CV. This is small CV for specific heat, and this is molar heat capacity at constant volume. And at constant pressure, it will be Cp is equal to small cp into m. So Cv and Cp are molar heat capacity at constant volume. At constant volume and at constant pressure. Relation between Cp and Cv is Cp minus Cv will be equal to R, and its value will be 2 calories, and on converting in joule it will be 8.314 joule. This is the relation between Cp and Cv. Now, ratio of molar capacities. Is Cp upon Cv will be equal to gamma. Gamma for monoatomic gas the value of gamma will be equal to by 2R and 3 by 2R. So its value will be 1.66, and for diatomic its value will be 7 by 2R on 5 by 2R, and the value of for diatomic gas the gamma will be equal to 1.40, and for triatomic it will be 8R by 6R, so its value will be 1.33. So these are the ratio of molar capacities for different types of gases. For monoatomic it is 1.66, for diatomic it is 1.4, and for triatomic it is 1.33. Now, liquefaction of gases. A gas may be liquefied when by the application of high pressure or by cooling effect or by lowering the temperature. So by lowering of temperature or by cooling effect or by applying of high pressure, a gas can be liquefied. Both of these conditions can be applied together, or by only by one application we can convert gas into liquid also. So the permanent gases like hydrogen, nitrogen, oxygen and argon have low values of Tc. So uh, these gases cannot be liquefied. If low values of Tc and it cannot be liquefied by the application of pressure, because there is small intermolecular forces or no intermolecular forces. So by applying of pressure, it cannot be liquefied. Even after so there will be no effect of pressure because there is no intermolecular forces, so these gases cannot be liquefied and these are permanent gases. But in gases which are having large forces, such as ammonia, sulfur dioxide and water, these can be easily liquefied because these have higher intermolecular forces and they have high values of Tc. So the gases can be liquefied easily. Now the methods of liquefaction. How a gas can be liquefied? First is Linde's method. When a gas is allowed to expand, adiabatically process, in adiabatic process, the it doesn't change, it doesn't transfer the heat. That process is called adiabatic process. When a gas is allowed to expand adiabatically from a region of high pressure to a region of extremely low pressure, then it will accompanied by a cooling effect, and by this effect a gas will convert into liquid. So in Linde's method, when a gas is allowed to expand adiabatically from a region of high pressure to low pressure, accompanied by a cooling effect, the gas can be converted into a liquid. The next method is Claude's method. This method is based upon the principle that when a gas expand adiabatically, a gas expand adiabatically, against an external pressure, it does some external work. Against an external pressure, it does external work. External work means it will lose its kinetic energy, and after losing this kinetic energy, the temperature of the gas falls. Temperature will get lowered and it will cause a cooling effect, and the gas will convert into liquid. So, in Claudius method, when a gas is expanded adiabatically against an external pressure, it will does an external work, and this external work is done at the cost of its kinetic energy. That will cause lowering of temperature, and this lowering of temperature will cause cooling effect, and the gas will convert it into liquid. And the third is by adiabatic demagnetization. Now, uses of liquefied gases. Liquefied gases are used in many ways. The first is liquefied ammonia and liquid sulfur dioxide are used as refrigerants. Liquid carbon dioxide is used in soda fountains. Liquid chlorine, as we know, it is a bleaching agent. And disinfectants. Liquid air is used in rockets and jet propellants. And bombs. In these things, liquid air is the source of oxygen. It provides oxygen for their process. Compressed oxygen is used in welding. And compressed helium is used in airships. So these are the uses of different types of liquefied gases. Now the last topic for the chapter is inversion temperature. The inversion temperature is the temperature at which a gas neither shows cooling effect and no heating effect. Or no cooling effect. The temperature at which gas shows neither cooling effect nor heating effect, that is Joule Thomson coefficient, inversion temperature is mu is 0, and below this temperature it shows a cooling effect, and above this temperature it will show heating effect.